two vectors in R3, A and B. I will call the cross product of these two, vector C. That will be another vector in R3, and that vector is basically explained by the diagram you're just looking at right now. The vector, the cross product vector, geometrically, computationally, I just describe you the process how to find that vector. It's not an easy process. You'll try this a few times. We'll try this a few times together. You will pick it up. It's after you just do it a few times, it's a piece of cake. Geometrically, it is a harder concept. Geometrically, the cross product vector, it's the vector. Just compare this with the dot product, which for two vectors returns a number, whereas the cross product returns another vector. And that's the one which is jointly perpendicular to your original A1 and A2. So if this is my A vector, this is my B vector, this is a cross product vector. It is jointly perpendicular to my original two straight away. You see, you don't have to solve any system of linear equations. You don't have to do any... When you solve that system of linear equations, there was also some sort of obscure step when I just chose the third unknown as I wished to be one. Something I don't think any of you understand fully yet. So it's another thing which I owe you, another explanation which I owe you. So, but this time, you don't have to solve anything. If you just plug the numbers into the formula for the cross product, your joint perpendicular vector will just come up immediately. I mean, if you finish everything, every computation involved in that. Now, not only the vector itself, not only the direction of that vector is important. The direction will be the vector perpendicular to my two original ones. So my C vector will be perpendicular to A and B. The other thing which is interesting about the cross product is that if you compute the length of the cross product, it will also have some interesting geometrical meaning. The cross product length is the product of the lengths of the original vectors times the sine of the angle in between. Here's my theta angle between my vectors, and the length of my cross product will be something like this. Geometrically, let me ask you this. If you have a construction like this based on two vectors A and B, and if you multiply the length of this side, and the sine of the angle in between, elementary geometry says to us that the value you come up with will be, well, it will be the area of a triangle if you halve it. But if you don't halve it, that will be of the parallelogram. So it's another good byproduct of the cross product. The length of that vector, not only the direction is important. Right now, we're only after the direction, by the way. We need the direction to our task of finding the distance. But not only the direction actually gives some interesting information. The length of the cross product also returns a lot of interesting information. That will be the area of underlying. That will be the area of underlying parallelogram. Here it is. It's a very deep result, in fact. That very convoluted computational process I described on the previous slide, if you compute the length of that, that returns the area of this parallelogram. It's not an easy proof. I mean, I'll leave it I'll leave it out of this topic straight away. I mean, it's not an easy proof, but it's elementary one. It's not a part of the linear algebra. That's the other reason why I'm not discussing that. It's a very deep result which is worth remembering. You can't come up with this easily. The length of this cross product vector gives you the area of this underlying parallelogram. Now, I'll finish in a minute. Before I finish, I want to ask you this. There is ambiguity in my way of describing of a cross product. I said it's a vector which is jointly perpendicular to my given two AB, and it's a vector which length is the area of the parallelogram based on those two vectors. It's not the unique description. There is another vector which will match the same description equally. The one which goes down. This vector. So it will be a reasonable question from the class right now, which one I mean, the bottom one or the top one. The answer to this is given by this line. The vector of cross product, together with the original two vectors A and B, A, B, C, they should form what is called the right-handed triple. Meaning that there are different definitions of the right-handed triple. You can go Wikipedia. It will have lots of demonstrations, beautiful ones, with the right hand, with the thumb, and many other ways to remember what the right-handed triple is. I'll prefer this one. If you imagine yourself sitting on the tip of this vector and looking down along this arrow, yeah, you can. I hope you can imagine that with your powerful graphic chip. If you're sitting on the top of this vector and looking down, you should see the turn from the first to the second counterclockwise. If you see it that way, this is a correctly chosen vector. If you try to do the same procedure from down here, then you'll be looking up. The turn from A to B will be clockwise. That's why you disregard that vector. Or, in fact, you can keep that vector if you take the cross product in the opposite direction. So if you take B cross product with A rather than A cross product with B. And then this dashed vector will be the result of that cross product. That's the first example of the operation, by the way, which is not commutative. When you flip the vectors around, it gives you a different result. Well, it gives you negative. Sometimes we call this anti-commutative.